And thank you for joining the Alexandria Library for tonight's webinar, Land Use and Climate Change. My name is Megan Zimmerman, and I'm an adult services librarian with the Alexandria Library. If you have comments or you need to contact me with technical issues, I ask that you use the chat box. If you have questions for tonight's presenter, please use the Q&A feature so that we can distinguish between comments and questions posted. And we do have time at the end to respond to those questions you give us. This event is being recorded and will be made available on the Alexandria Library's YouTube page under the Sustainability series. Our speaker tonight is Dr. Adam Terando, who is a research ecologist with the U.S. Geological Survey at the Southeast Climate Adaptation Science Center. A geographer and climatologist by training, Dr. Terando received his PhD in geography from Pennsylvania State University. His work with the USGS Southeast Climate Adaptation Science Center focuses on the impacts of global change on ecosystems in the Southeast and US Caribbean, and on the complex human-environment relationships that drive these processes. The goal of Dr. Terando's research is to gain insight that will benefit the public and natural resource managers in their efforts to respond and adapt to rapid global climate and land use change. Dr. Terando is also the federal coordinating lead author for the U.S. National Climate Assessment's Southeast chapter. Dr. Terando, thank you so much for being with us this evening. We look forward to your presentation.
Great. Thank you, Megan. Thank you for having me, and really appreciate the opportunity to get to talk with you all. So I'm going to go ahead and share my screen. And okay. This talk tonight is almost 3 talks in one, and I'm going to try to do it in 30 minutes, so we have lots of time for discussion. So let's go ahead and get right to it. So I'm going to be speaking tonight about land use and climate change and how the two things are linked, and particularly in the U.S. but even more so in the Southeast, in which for tonight's purposes I'm going to include Virginia, Northern Virginia, in the Southeast region. And so just first of all, who do I work for? So I work for the U.S. Geological Survey, which is actually headquartered just down the road from y'all in Reston, Virginia. And I work for a group called the Climate Adaptation Science Centers. And so our mission is to deliver science to help fish, wildlife, water, land, and people adapt to a changing climate. And you can see the region where I work is in the Southeast. These are kind of fuzzy boundaries. So sometimes I work in Virginia too. Sometimes I work all over the country or all over the world. Okay, so why are we here? What are we talking about here? Well, the Earth is warming. I think we all know this and appreciate this. And why is the Earth warming? Because of something called the greenhouse effect. Something else I think probably everyone or most people are at least have heard about by now. And so what actually is the greenhouse effect? Well, it's this physical process by which we absorb radiation from the sun. It goes through the Earth's atmosphere. And the really sort of interesting thing about the physics involved here is that this radiation or this heat, this transfer of energy that reaches the Earth's surface from the sun passes through relatively undisturbed and is able to heat up the surface of the Earth. Now, normally that radiation would then just re-radiate back out to space, and you would have some sort of energy balance if the Earth had no atmosphere, and that would result in an average temperature of the Earth of about 0 degrees Fahrenheit, which is very cold. But we have greenhouse gases in the atmosphere, particularly carbon dioxide. So Earth's returning energy is able to actually excite carbon dioxide molecules, and it's harder for those energy photons, which are those weird quantum particles that have dual sort of particle and wave properties, to then exit the atmosphere and re-radiate back out to space. They sort of get recycled around in the atmosphere and near the surface of the Earth. That warms up the temperature more than it would be otherwise, and that heats the atmosphere and heats the Earth, raising the Earth's global climate temperature. That's the greenhouse gas effect, the greenhouse effect in a nutshell. And that's a good thing. That's what makes life habitable on Earth. Otherwise, we would be an ice planet. But we are now, humans are now changing this greenhouse effect. We are forcing the system into a new equilibrium state by digging up stored sunlight, stored carbon, burning it for fuel, for energy, and particularly for things like transportation, which is a main theme I'm going to talk about tonight. And so just to give you a sense, I really like showing this figure that Noah put together to give you a sense of what's the amount of the change that humans have enacted on the climate system and on that carbon cycle so far. So this is an animation showing measurements of atmospheric CO2 over time. So on the left here is going to be, as I start this animation, you see different measurements starting in 1979, 1980. And you can see this sort of seesaw pattern going up and down, particularly over here on the left, we're showing it on these latitudes. In the Northern Hemisphere, we have a much larger seasonal swings in atmospheric carbon dioxide. And that's because we just have more land mass in the Northern Hemisphere. So that's just a season showing up where you're getting leaf on and leaf off. So in the wintertime, you have no leaves on the forests and in the grasslands and in the Northern Hemisphere. That means there's going to be less carbon dioxide for plants to absorb versus the summer, all those plants and all the trees, they absorb more carbon dioxide. But you notice overall the levels are increasing as we burn more carbon dioxide. So I'll keep showing that here. So you can see as we move through time, on the right is showing one measurement from Mauna Loa Observatory, which is sort of our best measurement we've had over the longest period of time. So now we're going to go back in time, though, back using proxy records of CO2 that's trapped in ice cores. And you can actually measure the tiny little bubbles that are frozen in ice and then get a pretty accurate measurement of what the concentration of carbon dioxide was in the atmosphere going back many years in the past. So you can see that we still have the same amount showing here, but the scales are now changing over here in the time. So now we're going back 1,000 years. Okay, now 2,000 years into the past. And we're going to switch the time scale to thousands of years in the past. Now we're showing the ice ages start showing up. 50,000 years, 100,000 years, 200,000 years, all the way back to 800,000 years where we have really good records of atmospheric carbon dioxide concentrations. And now you can really see, based on that, how much carbon dioxide how much carbon humans have really put into the atmosphere. And in geologic terms, this is really an instantaneous sort of bomb that we've released into the atmosphere in a very, very short amount of time. So to the point where carbon dioxide in the atmosphere is now higher than at any point in at least the last 2 million years. This causes the planet to warm. There is now more energy that will be that is harder to escape out to space, and so that will warm the climate. And it really results in a lot of changes to the climate system and then sort of knock-on effects, but we focus on 3 big changes here. 1, it gets warmer. That's the big one. 2, it rains harder. And 3, the seas rise. So when we say that the Earth is getting warmer, I think this is the one we're probably almost familiar with, but again, sort of thinking about the scope of the changes we're talking about here. This is from the most recently released IPCC Intergovernmental Panel on Climate Change report, the 6th assessment report from Working Group 1, which is the Physical Science Working Group, and the Summary for Policymakers. There's all your acronyms right there. And so you can see that over the last couple thousand years, you see the temperatures fluctuated up and down, maybe a slight decline in the little ice age. And the rate of warming we're now experiencing is unprecedented in at least the last 2,000 years, and could be, and probably is more like 6,000 years or so since we've had any sort of rates of change like we're experiencing now. And we can really only explain this when you account for the amount for the large increases in concentrations of greenhouse gases in the atmosphere that I talked about. If you take those away, which we're able to do through computer models, so sort of like a simulated experiment, this, if you think about it like a lab experiment, this would be the control experiment in the green here, where we show simulated what would the climate be like if we didn't add as much carbon and other greenhouse gases as we're adding, versus here, this is sort of the adding a stimuli. So humans are adding a stimuli to the Earth's climate system by adding all this extra greenhouse gases to the atmosphere, and that's causing this really rapid increase in global temperatures. We see this in all sorts of ways. Here's just an example of that. This is the ratio of daily record highs to daily record lows recorded across the United States. And if the climate wasn't changing in any significant way, this would be a very boring graph. Because you would expect the same ratio. On the y-axis here is the ratio of daily high temperature records to daily low temperature records. So if there's more daily low record temperatures, then you get more blue bars. More daily record high temperatures, you get more red bars. And so you can see that we're getting many more daily record high temperatures now than record low temperatures. And we expect this to continue into the future. So this is showing how much more frequent do we expect extreme events to become in the future. So right now, say a once in 10 year extreme heat event, so say a 10% chance of such a thing occurring now, depending on how much warming we have in the future, say we ended up with up to 4 degrees Celsius more global warming, well, that once in a 10-year event basically becomes an every year event at the highest levels of warming that are possible by the end of the century and beyond. And the same thing with the 50-year event. So in a really extreme event, once in 50 years, if you go to the highest future potential warming levels, that becomes something that could happen in about 4 out of every 5 years into the future. So about 80% of the time. So we're already seeing some of these changes, again, showing things like extremes. You can see this for hotter nights in the Southeast. We haven't really seen too many changes in extreme daytime temperatures, but so far, and a lot of that's, we can get into reasons for that if you're interested, but we are definitely seeing that in the southeastern region for nighttime temperatures, much more very warm nighttime temperatures. The second big change is that it rains harder, okay? And so why is that? Well, it's another sort of basic physics principle in that a warmer atmosphere will have more water or water vapor in it. Okay, and so what that means is that we have this relation called the Clausius-Clapeyron relation. So the amount of water vapor, that's what's shown on the graph here on the right, the amount of water vapor in the atmosphere increases as temperature increases. And that rate of increase in water vapor is about 7% increase per degree Celsius of warming at the temperatures we're experiencing here on Earth. So that means that when you are able to rain out that water vapor, when you do have rain events, if you're in sort of a warmer, juicier atmosphere, you can really get much more extreme rainfall events. This is probably something I think we've all experienced or seen happening so far. And again, if we look to the future in terms of depending on how much warming we have in the future, which again is conditional on how much more carbon and greenhouse gases we release into the future, those extreme rainfall events really start becoming less extreme and more the norm, to the point where something that happens, say, once every 10 years, a 10% chance every year, it could occur 2.7 times more frequently in the future. And not only that, but that sort of extreme event becomes a lot wetter too. So it happens more frequently with more rainfall associated with it. Okay, the last big change I'll talk about here for climate change is sea levels increasing, okay, the oceans rise. Basically, that's a function of melting glaciers and ice caps from Greenland and potentially from Antarctica. And also the expanding volume of the ocean. You know, as a liquid warms up, it expands. Again, basic physics. So this is showing the amount of sea level rise we've had so far on the left, and also on the bottom here. And this is showing it in meters, and then different potential changes in sea level rise in the future. Again, really dependent on how much greenhouse gases we emit. One really thing to keep in mind with sea level rise is there's a really high amount of inertia in the system when we talk about that, because it takes a lot more time for the system to come into equilibrium with the warming we have in the climate system. So analogy I like to use is I used to have a refrigerator that would ice over all the time. And so I would have to open up the back panel and take a blow dryer out and thaw out the ice that had built up. Well, that's very hot air I'm blowing on ice, but it takes a long time to actually melt that ice, even though you're blowing really hot air on it, because it takes a lot of energy to actually go into melting that ice and changing it from that phase transition from solid to liquid or to gas. So the same thing is happening here. It takes a lot of energy and a lot of time to actually melt something like Greenland. But then it's sort of an inexorable change for it to come into equilibrium, which is what's showing here that by 2300, even if we really limit greenhouse gas emissions to not much more than what we're doing now and stop emitting future greenhouse gas emissions, we're still in for a good amount potentially of sea level rise into the future. This is showing out to 2300. It just takes a long time to get there. So something to keep in mind when we talk about sea level rise now and future generations. Okay, so then how this then affects different aspects of living along the coast. So this is showing changes in sea level rise in the US, in the blue dots, the time series here. One big thing that we see is this sort of sunny day flooding events where you get these king tides or these high tides that cause, some people call it nuisance flooding. It's not really tied to any storm or anything like that. It's more just tidal flooding. And we're seeing that these tidal events are really increasing in frequency along many parts of the coastal US. And those recurrent flooding events, which right now are increasing in frequency, but still sort of rare, are projected to become the norm over time as sea levels rise. And then the last sort of example of this is showing, again, what happens when you combine these effects. So here's showing Hurricane Florence, an example from North Carolina, and showing the amount of rainfall we got from that storm. So there you sort of have the perfect storm, if you will, of potentially changing hurricanes, particularly in terms of the intensity of hurricanes, a warmer, wetter atmosphere that can juice up the amount of rainfall that falls. And then you combine that with rising sea levels, and you can get some really gnarly effects in really vulnerable areas as the climate warms, as the planet warms. Okay, so the world realizes this. We have talked about this problem. Scientists have alerted the world to this problem for decades now. And so we've come up with different policy options and potential solutions. The Paris Agreement being the most well-known. Here's where they, during the Paris conference in 2015, they lit up the Eiffel Tower, saying with a goal of limiting warming, human-caused global warming to 1.5 degrees Celsius. That was the stated goal. So how do we actually take care of that then? What are the ways that what do we target in terms of reducing greenhouse gas emissions? Well, in the US anyway, which is the second largest emitter of greenhouse gases in the world, a good chunk of our emissions are taken up in just two sectors, okay? And that's electricity generation and transportation, okay? So you can see that those account for over half of all greenhouse gas emissions in the US. So if you're, say, a government agency and looking to promulgate regulations that will reduce greenhouse gas emissions, you might target, say, fossil fuel power plants in the US. And so you can say, well, that's pretty daunting, but there's over 3,000 of those. And so trying to ratchet down emissions from that source is a challenge, right? But we can compare that to the challenge of, say, regulating passenger vehicles, okay, where there's some 270 million passenger vehicles on the road in the US, the vast majority of which use gasoline or diesel. So taking care of all those sources of emissions become, you can see the orders of magnitude greater and challenging in changing, not just regulating, say the auto manufacturers, but just the system that's built up around this particular transportation system. And this is sort of gets into the second part of the talk now. So, we drive a lot in the US. It's kind of an understatement. This is showing the annual vehicle miles traveled in the United States going back to the early 70s. And we're now at over 3 trillion vehicle miles traveled every year in the United States. This is the same figure, but for Virginia, and I've updated it to the end of last year. And so these numbers are in millions of vehicle miles traveled. So this is actually 6.5 billion vehicle miles traveled, for instance. And obviously you can see COVID, right? COVID shows up very clearly there, but so does recovery from COVID, however you define recovery. And so you can see that is sort of shooting right back up. We're not really seeing a trend where this is that decline we saw is a permanent thing. So far, that trend is moving back towards where we were pre-COVID. And so therefore, transportation accounts for about half of Virginia's total greenhouse gas emissions. So it's a higher proportion than the United States as a whole, which was about 30% of greenhouse gases. In Virginia, it's up to about half of the total emissions. And so one way to think about this is like, well, how does that compare to other countries in the world? So Virginia's transportation emissions are about 52 megatons of carbon dioxide equivalent every year. And that's for about 8.5 million people. That's the same as the emissions from all sectors for 36 countries around the world. That equates to about 15 million people. So again, about twice the number of people, but all their emissions combined. So that's power generation, transportation, agriculture, all of it. So in the US, when we're talking about greenhouse gas emissions and if you're talking about reducing those, transportation is really a huge source of those emissions. And as we continue with our, system we have, which is sort of built around driving, transportation system built around driving, we add more people to the region, and those people are likely to drive. So people are moving here quickly, and so it's going to be a challenge. Okay. So why are people moving here quickly? Many reasons. One reason that's really just a really basic reason is, again, now I'm talking about sort of the Southeast at large, not just Virginia or Northern Virginia. Well, there's a favorable climate. The warmer climate of the South continues to drive in-migration to the region. This is sort of a complicated figure, but I really like it, so I'm going to show it anyway. This is from a paper showing the utility, sort of the theoretical utility of that people might derive from living in different cities with different climates. So on the y-axis here is January daily maximum temperature. On the x-axis is the July max heat index, okay? And so you see, if you map all these different cities, so for instance, here's Santa Barbara, here's Wichita, here's Orlando, here's Duluth, Minnesota, Minneapolis, Minnesota. So obviously Duluth is pretty comfortable in the summer, pretty darn cold in the winter. And so there are these estimates of, say, what is the utility people derive from living in a place like this, because you value both, comfortable summers and comfortable winters. So Duluth, in this case, pre-air conditioning would have about the same utility as, say, Riverside, California. But at the same time, Orlando would have a much lower utility than Duluth, just because without air conditioning, the summers are just unbearable. Now, you shift and you include air conditioning, and you can see that a lot of the fastest growing cities in the US, their utilities suddenly, and that's what these dashed lines, they suddenly jump, and they become equivalent to what these sort of higher utility and sort of Mediterranean type climate cities would have experienced pre-air conditioning. So this really bears out a lot in the US. And so this, you can actually map then what would be the expected contribution to population change and in-migration within the US due to these more favorable climate conditions. And you can see how it sort of wraps around the southern tier of the United States. But that's not the only thing that drives sort of then, our population patterns, how we're actually living across the US. There's been big changes that are then foster, amplify, exacerbate our transportation system as people move into the Southeast. And so one way to think about this is the idea of what is a suburb and how have suburbs changed over time. This is an example from the 19th century in Chicago, in Riverside, the town of Riverside. And really you can kind of see this desire for this pastoral ideal in our suburban environment. The idea of almost replicating, say, you can see the pretty leaf-lined trees or streets with sidewalks, large homes. The idea was at its heart to sort of mimic an English manorial estates, really, with these large manicured lawns that were themselves were hearkening back to sheep grazing, that pastoral medieval life in England. And as that became sort of the norm and transferred over to this model for suburbia, it really fit in well within the introduction of the automobile, in terms of cars being able to facilitate the segregation of land uses. So you're keeping houses separate from any sort of businesses and schools and everything in industry, and allows really long trips. So you can have larger lots and you can get from one land use to another quite easily. So we can see this change then in cities across the US. So this is showing 3 different city or metro areas. So this is Chicago, Boston, and Atlanta. And the heat maps here are showing areas that are less connected by street networks versus more connected. So if it's red, it's less connected. And if it's blue, it's more connected. Think about more connected as being like a dense grid pattern that you might see, sort of like DC, downtown DC, versus, say, if it's red, it's going to be more like cul-de-sacs, pure cul-de-sacs everywhere. So in Chicago, you had this large pre-automobile core and a preference for high connectivity and suburban development. So you have lots of blues and greens. These are your classic streetcar suburbs or railroad suburbs where you sort of radiate out from the central business district. Boston has sort of a mix of pre-automobile core, where really you were looking at the city being developed around just a walking city, if you go back to, say, the 1700s or even earlier. And you have a mix of high and low connectivity suburban development. Versus Atlanta, you have this preference for really low connectivity suburban development. It's really driven by the automobile and that segregation of land uses. So we kind of get this feedback loop here, which is driving then our transportation system. So we have this preference for a particular type of suburban pattern as cities grow. So car ownership and use increases. That leads to more traffic in cities that are still constrained by geography. People don't like to, say, commute more than 30 minutes at a time. So you have to adjust and people that will generate more traffic on roads. So that leads to incentive to modify cities to accommodate the increase in cars. People don't like being stuck in traffic. And so cities are increasingly optimized for movement by car rather than other forms of transportation. So you get this, and that leads to more car ownership because it becomes easier to drive than it does to, say, to walk or ride a bike or take the bus. And all that means that particularly in the areas that are experiencing the most population growth in the last several decades, suburbanization is what urbanization is in the Southeast US. So we see low density development, but it covers a really large spatial extent. So using an example from North Carolina here. So again, back to vehicle miles traveled per person for each year. This is showing for the US about 10,000 miles per person per year. In North Carolina, for instance, it's quite a bit more than that, up to close to 13,000 miles per year. And so we've developed our cities since World War II in the Southeast as people moved here with this pattern. And so this is showing the zoning map for the city of Raleigh. And you see this huge swaths of it are set aside only for houses, which means that to be able to get to school or get to work or get to the store or get to a park, oftentimes you have to drive there. The consequence then, back to climate change, is that we have more emissions per person. So this is comparing my area, Raleigh, North Carolina, and say Raleigh, Durham, Chapel Hill, that whole area, and where there's about 1.2 million people, to say Barcelona in Spain, a very a metro area city with a very similar population, but a very different urban pattern that's built up in a different way. So Raleigh covers, and we call it the triangle, covers a much larger area, about 10 times the area, and has close to 10 times the carbon footprint per person when it comes to transportation. Again, because we've sort of built this system that requires getting around by automobile. So some of the work I've done then is, what happens if we keep this up, if we keep this pattern up? And so we worked on this in a mod using some models and produced this paper called the Southern Megalopolis. And the idea was to think about like what would happen to growth of urban areas or suburban in the Southeast under sort of a business as usual scenario. And it was nice. I got an article written about it in your hometown newspaper, in the Washington Post. But what we were basically trying to do was to simulate these different types of suburban growth that are dependent on the automobile. And that's these, so you can see the types of growth, spontaneous, these sort of patterns of growth we were simulating. This is a photo then to give you an example of what it would look like. So this is showing Northwest Raleigh in the early 90s. And then by the 2010s, you can see this is the exact same area. You can see how all this growth kind of picks up. So that's what we were trying to simulate. And we found that actually just using the density of the road network did a pretty good job of characterizing this pattern of urban sprawl. And you can see all the different cul-de-sacs popping up here. And so when we did that, after we characterized all the urban area in the Southeast, here's Northern Virginia up here, here's say Florida, here's Raleigh. You can see as we simulate the probability of suburbanization into the future, you can see how it kind of spreads based on those patterns of growth that we've seen in the past. And we can see that, and our projection was, if again, under business as usual, without any changes, we could see really large increases in suburban growth by the middle of the century. And you start to get these sort of merging of metropolitan areas. So this sort of Piedmont megalopolis connecting, say, Raleigh to Greensboro and Charlotte, all the way down to Atlanta. And other areas in the Southeast where we didn't see those patterns. So say like Mississippi, where we're not seeing that type of growth. That's where you see things like economics playing a role, where you have other factors besides just, say, a warm climate that's driving population increases. Okay, so the third factor in this is that, I've been talking about climate change this whole time, but a big reason that we were doing this study was because we were interested in how this is not only a problem for the climate, but has huge implications for biodiversity and wildlife. Okay, so some of the effects that we showed from this study were large-scale habitat loss and a much more fragmented landscape when it comes to habitats. So the change in our study showing large increases in urban areas, but for any other types of land cover, whether that's agriculture or forests, grasslands or wetlands, we would see these decreases in the amount of those types of land covers in time, as you would expect. So for different species, that has different consequences. My colleague, Jen Costanza, she did this nice study. So using our urbanization data, they then modeled, well, how would, say, a species like black bear be able to move across the landscape? And this sort of thing becomes important, again, tying it back to climate change, because one way to try to adapt to climate change is to protect, identify, and then conserve different landscape corridors that species and wildlife could use to move if they have to, if, say, their original habitat becomes less desirable or less fit for them as the climate changes. So say as it gets hotter, or as you start to lose coastline, those are all things that could drive species to need to be able to migrate. So looking at these migration corridors is really important for an adaptation strategy. But then also then say, and that's what these lines are showing, different pathways that, say, bears might want to take to reach different habitat cores. But the urbanization or the suburbanization starts to get in the way. So that's what's showing with the orange or the red lines, is showing corridors that start to get cut off for wildlife into the future if suburbanization proceeds in that way. So you can think about these corridors conserving different areas. This is a big effort amongst the government and NGOs, but it can be really difficult to create these conservation corridors to adapt to climate change as more urbanization, suburbanization occurs. Okay, so what are some solutions? Wrapping up here, decarbonization options. If transportation is really a big issue when it comes to carbon dioxide emissions, what are different ways we can address this? Well, probably the way we're most familiar with when we talk about transportation is to switch to electric vehicles, right? That's probably the main thing we think about. But there's things to consider. There are consequences of going that route or putting most of your eggs in that basket. So some people call this greening the status quo. So we're not really going to change anything about our transportation systems. We're just going to try to squeeze out the emissions that come from the 270 million cars and light duty vehicles that we have on the road. This can be tricky though, because really transitioning a huge amount of this vehicle fleet, which right now relies on gasoline or diesel, is an enormous undertaking. And to be able to do it in a way that where we can still meet our climate goals, it becomes really daunting. Okay, so one thing, this is a nice study showing that to have any sort of chance to still hit, say, an 80% reduction in CO2 emissions by the middle of the century, 2040 is probably the absolute last year, and by which in the US you would have to switch over to only selling electric vehicles. So no more gasoline vehicles would be sold after that point, because it just takes that much time to transition the fleet over from one vehicle type to another, one powertrain to another. And so that becomes really difficult to do. And when you're talking about that, obviously the earlier you start, the easier the pathway is, but it's no small feat to be able to do that. And of course, that doesn't speak to anything related to the other impacts from having the kind of transportation system that we have now, and such as sort of, say, the wildlife or biodiversity impacts I talked about. So that is one strategy. We could work to transition the fleet over to electric vehicles. We are actively doing that. Of course, there's many bills in Congress that talk about that. And we could continue with this the current land use pattern that we've sort of developed over the last 50, 60 years. But there are other pathways as well. So this is showing one example of that. And basically this shows that just having a different land use pattern where you are not, that doesn't sort of require people to use a car to get around, can really reduce the greenhouse gas emissions, the carbon footprint of people and of a family, okay? And this is another strategy that really gets down to the local level, to cities that can take this strategy. This is probably not going to be a top-down strategy from the federal government. There can be sort of carrots and sticks that are applied, but it's really going to occur at the local city, municipality, county level to do these sorts of things. Things like, allowing for slightly higher densities and a mix of uses. So say allowing a corner coffee shop or grocery store, or even a corner bar within a residential neighborhood, and allowing those residential neighborhoods to have slightly higher density housing. So allowing, say, duplexes, triplexes, those sorts of things. Those can really reduce the carbon footprint of cities. But of course, those are no easy feats to accomplish either. So we're seeing this being implemented across in several cities across the globe, though. One of the most famous ones is in Paris, where the mayor has implemented a strategy they call it the 15-minute city, where the goal is that everyone in Paris should be able to meet their basic needs through a short walk or a short bike ride. So that's food, shopping, school, parks, entertainment, all those things should be within close enough distance that you can walk there or you can get there on a short bike ride. That is a major shift in thinking from, say, where we've been, as a society over the last several decades. But it is one that would lead to dramatically different results for the climate. So, we have choices. We can develop cities in such a way where we live closer together. Maybe this is the most extreme example of that. Or we can continue on the pathway we've had for the most part. This is showing the highway expansion plans for Houston, which would this sort of mega highway of, 25, 30 lanes chopping up the city, which sort of, amplifies and doubles down on the transportation system we've developed so far. And so I'll leave you with this image to think about in terms of which future will society choose. This is a highway in North Carolina. This is actually Interstate 40 going down to the coast after Hurricane Florence, where the highway turned into a new river temporarily, going down, meeting the ocean. So with that, I thank you very much, and I am happy to take any questions. And let's see, Megan, do you want to, I can go ahead and read the Q&A, or unless you had anything you wanted to say first.
No, thank you for this presentation. It's been wonderful. I do want to give the questions time to get answered. So if you want to go ahead and read those, that would be great. And we'll follow up after.
Sure, absolutely. Okay, can you share your slides, and can I use them in future presentations? Yes and yes. Just give me, say, till the end of the week, and I will send them to Megan, and then she can distribute. Or you can just contact me. I can, Megan, if you have a way to send out my email information, please do so. I'm happy to then share the slides with anyone.
I'll do that. Thank you.
Okay. Ellen also asked, what is the impact of methane release from permafrost areas? Well, it warms the climate. So methane is a greenhouse gas. It's a more potent, more powerful greenhouse gas than carbon dioxide, but thankfully it has a shorter, what we call atmospheric lifetime. So it tends to stay up in the atmosphere for less time than carbon dioxide does. It also has more sort of secondary effects in the climate system that cause more warming. So sort of some what we call positive feedback. And so yeah, methane is responsible for a significant amount of the warming, but it's not necessarily just from the permafrost. Most of it is actually from agriculture, but methane release from permafrost is a big concern. It's one of those things that could amplify the warming response depending on how quickly that methane gets released from permafrost. So yeah, it's a concern. It's I wouldn't go so far as to say it's sort of like doomsday scenario. I think maybe you hear that sometimes, but it is definitely a big concern in terms of methane release. It's an added warming effect on the climate system. Okay, and Ellen also asked, what is the impact of war bombs relative to the normal amount of carbon from non-war times? Okay, so if I can try to parse that. So the impact of war bombs, I don't know. I'm going to say, if I was going to hazard a guess, I would say not much, because it's just, I mean, the biggest, if you're talking about heat release, well, that's minuscule in the grand scheme of things. If you're talking about, say, tanks and airplanes releasing fuel and all that, that's still pretty small compared to normal greenhouse gas emissions, particularly because you have to think about economies are shutting down in the Ukraine and Russia. I assume that's what you're talking about. And economic depressions are really the cause pretty severe drops in carbon emission and greenhouse gas emissions. So hopefully I answered that well enough. Okay, and Ellen mentions that transportation in Alexandria is 36% of our greenhouse gas emissions. Yeah, and that doesn't surprise me that it's a little bit lower. I think because you guys in Alexandria have probably higher use of public transportation and shorter trips by walking or biking than, say, many other areas in Virginia, since you're a more urban area with a sort of that dense walkable core, and you have the metro there. Okay, James asks, is there any way to remove carbon from the atmosphere in meaningful quantities? Potentially. This is obviously a huge research area and of intense interest from the governments of the world, because obviously if you could just suck CO2 out of the air, then it would be much easier to limit the damage from warming the planet so much. And it would mean you would have to make less changes potentially to your economy and your way of life. So we do not have the ability to do it right now, but there are many demonstration projects working on it. And I mean, another aspect of this is that the longer we take to reduce emissions by other means, either from fuel switching or changing, our transportation systems or our electricity systems, the more we will have to rely on carbon dioxide removal as a means to limit damage from warming. So yes. Okay, besides purchasing electric vehicles, reducing the amount of energy we utilize, etc., what are the other things you suggest we can do as individuals? Well, I guess it depends on what you want to see in your communities. Some of the examples I gave at the end, like say the Paris 15-minute city, that was a conscious policy choice by elected officials, and by the mayor who got elected by the populace at large. So if that's, say, an outcome that is amenable to you, then one way you could try to make that happen would be to say get involved with your local government or things like that, and encourage that sort of solution. So I think those are lots of times we do talk about individual actions, and then I work for the federal government, and we tend to get squeamish about suggesting policy options, particularly in USGS. And so I'm not going to say do this or do that, but I will just say that different policy options will require sort of a policy response, not just individual actions. So that requires people getting involved in the policy process if they want those things to happen. And those probably will have then much more impact than, say, your individual action, because then those policies can be applied to many, many, many people, not just your own self. Okay, so Kristen asks, knowing what you know about climate change, where in the US would you want to live in 2050? Okay, well, that's that response is obviously going to differ per person, right? Everyone values things differently. So when it's 95 degrees and very humid, as long as my air conditioning works, even when I go outside, I tend to not mind that so much personally. I know other people, such as the director of our program, who like that is probably their literal definition of hell, which is why they now live in Wisconsin, right? So, that's all going to depend on what you value. Obviously, certain areas are going to be more vulnerable to different impacts from climate change, particularly the coasts are going to really have to deal with some inexorable changes that are going to affect people living right along there. We saw this summer some of the effects of, every summer now, we're seeing pretty huge wildfires out west in certain places. And some impacts I think are not going to show up for a little bit and are going to be really big into the future, like extreme heat in the summer. So, I think all those things are really going to depend on what are you comfortable with yourself and how much risk are you comfortable with taking on. Okay, so Maeve asks, I appreciated your graph of utility of cities that takes into account air conditioning, making some areas more desirable places to live. Is there a way that you approach modeling induced demand due to highway expansion, right? To what extent can we predict public transit as a desirable amenity in this country? Okay. So, yeah, so modeling induced demand due to highway expansion. I know that there's a group out at UC Berkeley, that does this, and I think they're called like the Sustainable Transportation Institute, and they have some cool models that are doing that. So I guess short answer is yes, there are ways to do that, and those are being used more widely now. I don't know how widely they're being used in transportation departments, which maybe that's a topic for a different day. And then to what extent can we predict public transit as a desirable amenity in this country? I don't know. I honestly don't know how to predict that. I think there's a lot of factors that go into that. That's sort of why I talked about sort of the history of suburbs and showed those the example from English manorial estates. A lot of sort of like desirability is I think is sort of a function of not just personal taste, but sort of culture itself, and what's sort of seen as acceptable, unacceptable, what's seen as like legitimate and illegitimate, those sorts of things. So all those things are really hard to model and predict. And I guess that's more in the realm of urban planning in terms of trying to think through those things. Sorry, I don't have a better answer to you on that, Maeve. Okay, how does the environmental impact of suburbanization compare with the impact of living in a rural area? Well, there's probably different ways to answer that. I think if there were the same number of people living in rural areas as suburban areas, I would expect that rural areas would probably have a larger carbon footprint, at least. It's kind of hard to gauge in terms of total environmental impact, but there's fewer people that live in rural areas in the US than there are in suburban areas. So even if you have sort of the same accounting for similar income levels, if you're doing a like by like comparison like that, there's just more people in suburban areas. So overall it contributes more to at least the greenhouse gas emissions in the US. So it's sort of like, if you think about if people are going, suburban areas are urban areas, right? They're still part of urban agglomerations. And so it's just sort of thinking about the the plurality of people now have chosen in the US or have chosen for them suburban areas for where they're living. And that means that that's driving the most amount of the environmental impact. Okay, James asks, could we put space-based sun shields to stop some of the sun's energy from going to the earth to compensate for the increased CO2 gas concentration the last couple hundred years? Think on beach umbrellas in space that reflect back the sunlight. Yes, this idea has been put forward before. And so the answer is hypothetically, it is possible. Theoretically, it's possible. There are really significant consequences for doing that that people have discussed and thought about. So, you know, not least of which is you're not getting solar radiation, which is really important for, say, plants and agriculture. So whose sun are you going to block, right? So that brings up some really thorny legal questions then. The other part, so for a lot of these sort of geoengineering solutions, that's what these things are called. You know, sometimes the consequences, say unintended consequences, can be really bad as well. Another sort of well-known geoengineering solution that's been talked about is to release aerosols, more aerosols in the atmosphere. So one reason we didn't see much warming of the planet, say from about the mid 40s up to about the mid 70s and 80s, was because of industrial production, particularly in Europe and North America. And that produced a lot of these aerosol molecules that were able to reflect solar radiation, and that had a cooling effect. So sort of similar to James's point about solar umbrellas, but it was in the atmosphere. Well, when you know, Western countries started instituting air pollution laws like the Clean Air Act, the first thing that did was started to get rid of a lot of those aerosols, and that allowed more solar radiation to penetrate all the way to the surface of the earth, which led to more warming when you included the background increases in carbon dioxide and other greenhouse gases. So people have talked about geoengineering, adding more aerosols, but as soon as you take those away, if you don't also reduce carbon dioxide and other greenhouse gases, the warming, if those aerosols go away, the warming shoots up even more rapidly than what we're seeing now. So that could be a really bad consequence of that. So there's sort of like this is sort of where the precautionary principle as an ethical choice might play a really big role and become important, because you might have one, you know, solution, but it leads to a lot of other problems that you know, could be worse than the cure, so to speak. Okay, and Jenny asked, what effect do the wildfires have on climate? Extra heat and pollution, and then loss of oxygen created. Okay, so the main effect from wildfires on climate and global warming is actually from the carbon that's released, not from the heat of the fire itself, nor from oxygen. The oxygen cycle is just incredibly stable and hard to dislodge in any meaningful way. So Jenny, you can put your mind at ease on that front anyway. And the heat that it generates is just really infinitesimal compared to the whole Earth system and the amount of energy we receive from the sun. So the carbon is that gets released from burning all those trees and anything else is it's not a trivial amount. So that's actually one reason why, and the other thing I do in my job is I do a lot of work with what we call prescribed fires, so the intentional setting of fires. And there's two main reasons we do that in our region. One is to actually promote certain habitats that are dependent on fire, and for endangered species, they really require forests that have frequent low intensity fires. But also what that does is that reduces the fuel hazard and the risk of wildfire, because if you get a wildfire, it's much more likely to be a big conflagration, sort of what we call like a stand replacing or a crown fire that burns down the whole trees, versus say a prescribed fire that hopefully can be a little bit more managed and stays low to the ground and just burns those surface fuels without burning all the trees down as well. Okay, and it looks like this might be the last question. So can you think of an example of a time that US government action caused a large scale shift in cultural attitudes in the way that moving a majority of Americans away from cars or highways would be? Let's see. Yeah. I don't know of anything on the scale of moving away from cars and highway. Well, yeah, actually I do. It would be the interstate highway system, and that moved people towards cars. I think that is probably, yes, that's probably one I would say, is it moved Americans towards cars as the dominant mode of transportation, versus if you think back to the early 20th century, still the dominant form of long distance transportation was, was by train, streetcar, was by rail. There's a lot of cities that had electrified rails as a means to get around, and those were all torn up and replaced with cars. Now, of course, that was a symbiosis between government and private industry, but yeah, that would be the example. So it can happen. And I think we do have examples of government sort of being that leader in providing the signals in terms of, what do we think, sort of the system by which society operates. What sort of systems are we favoring? So good question, Anonymous, and thanks. We'll use that to wrap up the chat. I'll hand it back to you, Megan.
All right, thank you so much, Dr. Terando. This has been so interesting, and really good questions from the audience as well. I'll echo what somebody mentioned, that seeing those graphs really puts in perspective a lot of what we talk about when we hear about what carbon dioxide looks like in the atmosphere, and what that's really what that looks like over the long term. And I'm impressed by the coverage you went from covering what climate change is all the way to what that is looking like in our urban setting. So thank you. This has been a wonderful presentation. And James echoes that as well. So thank you all for joining us, and thank you for taking time to be with us this evening. Really
Thank you.
appreciate it.
Thank you. My pleasure. Take care, everyone.
All right. Good evening, everyone.